Okay, so let's pick up where we left off. All right, so now we're going to talk about gear trains. Okay? Okay, recall that if a set of gears satisfies the fundamental law of gearing, okay, its first order kinematic coefficient is constant. And you might recall this. We proved this if this is gear 2 and this is gear 3 and this is the input. You want theta 3 prime to be constant because you want these ratios to be constant. And we derived that in the last previous lectures there. Okay. So recall that Rj is the radius of gear J's pitch circle. So remember when you've got gears, there's 4 different circles, and the one you're always going to care about here is the pitch circle. Sometimes you'll deal with the base circle, and if you do, it'll be called RBJ instead of RJ, okay? And we also derive this relationship. If that doesn't look familiar to you, go back to the previous video in this topic, and you'll see our derivation of that. That relates to pressure angle theta, which only exists again in a set of gears, to the pitch and base circles. Okay. Okay. So since any set of meshing gears will have the same pressure angle, okay. Obviously, if two gears are mating, remember they have the same diametral pitch and the same pressure angle. So theta is going to be the same between, if theta 3 and theta 2, if you're going to distinguish that where theta is the pressure angle, it's going to be the same. It's just theta. So if up there you see R2 divided by R3, that's the pitch circle of this divided by the pitch circle of that. If you take this equation and do that, where you plug in 3 and 2 in there and divide those, then you're getting R base 2 divided by R base 3, and cosine theta will cancel because they both have the same theta. Okay, so we're going to add that relationship up there. So not only does the first order kinematic coefficient equal omega 3 divided by omega 2 and R2 over R3, but it's RB2 divided by RB3. Okay? And by the way, by that same token, that also equals the diameter of the base and pitch circle divided by the diameter base of its mating pitch circle. And it's also the circumference, right? If you times both numerator and denominator there by 2 pi, then that's going to be the circumference of the perimeter of both those circles, will also be the first order kinematic coefficient. Okay? Okay, so let's see if we can find other ratios that equal the first order kinematic coefficient. Okay, so recall also that for a set of gears to mesh properly, their diametral pitch, P, capital P italicized, must be equal. So P2 must equal P3. Or in other words, remember the definition of P is N divided by 2R. So these guys have to be equal. Okay, so by massaging that equation, the 2's cancel, and you get R2 over R3 is the number of teeth on 2 divided by the number of teeth on 3. And so we can add that to our little mix there. Okay, so remember we said R2 divided by R3 is N2 divided by N3. We just proved that. Okay, so that's honestly probably the most useful one, right? Because if you wanted to find what is the first order kinematic coefficient, or what's the ratio of input or output to input angular velocities, which is always what you care about when you're dealing with gears, you don't really want to find the pitch circle because, like you said, that's very difficult to find and very difficult to measure for any given thing. And certainly the circumference or diameter of those are difficult. And the base circle would be equally hard to find, the radius of, because you'd have to back calculate the involute profiles on each of the gear's teeth to find the base circle, and that would be a nightmare. So it's very difficult, but it's easy to count teeth. Right? So if I just gave you a gear, you just count the teeth and boom, you do that for both gears, take the ratio, and you have that angular velocity. So of all these relationships we've found so far, the teeth, counting the teeth makes the most sense. If I said find the angular velocity ratio, boy, you'd be smartest to count the teeth. Okay? Okay, but there's other ratios here that we can find that are interesting. Okay, so let's find ratios of moments here. Okay, so let's see these equations. So if a moment m2 is imposed on gear 2, as shown below, the force acting on gear 3 along the line of action can be calculated according to that. Now, one thing I want to point out, this is for quasi-static conditions. So what I want you to imagine is imagine this gear is like bolted down. It can't move. It's not allowed to move. It doesn't have a velocity. It doesn't have an acceleration. It's just bolted down. And we're putting this we're cranking a moment on this. And this one isn't moving either because that's bolted. You're just cranking a moment on it. If you crank that moment on it, then it's a true scenario that m2 divided by this base circle radius will be the force along the line of action, or this pressure line, right? So that's F, okay? All right, and so, okay, and we know, since we have this, this max force here, we can find there's a radial component, or a radial component along the radius and a tangential component, okay, or a normal component, okay, that breaks this force up. But whenever a gear, is twisted to drive another gear, it's important to know the force goes along this pressure line, right, with the two components, okay? And so you could take this, that's the magnitude, and times it by sine of the pressure angle to find the radial component, or times it by cosine theta to find the tangential component. So that's where you get the two different components. And by the way, remember, for helical gears, there's also a component that comes out of the plane at you, which is the mess, okay? But for spur gears, they don't have that. They just have radial and tangential components. Okay, so recall this. This is the relationship between the base circle and the pitch circle for any gear where you have the pressure angle theta. And knowing that, you can say, well, hey, let's look at F tangential here. F tangential was this. And notice here, RB2, divided by cosine theta is R2. So you can just replace these guys by this. So if you take M2 divided by R2, it's F tangential, which makes sense because look at the diagram. M2 divided by R2, which is the green circle radius. Put a moment on divided by that radius, you're going to get that force. Okay, that's usually the force lots of people look at. Okay, so we're just going to keep that here on the table here. I promise I'm going somewhere with this, okay? Now let's look at some other relationships. M3, in other words, the M that would be imparted on this gear would then be F, which is this one, the force imparted on this by M2, times RB3. Okay, so that's the force that's going tangent to the orange circle, so you times it by RB3, that's M3. Okay, so, and then if you take this, okay, then you could take M2 divided by RB2, okay, which is right here. Remember, we showed that F equals M2 divided by RB2. Plug that in for F, and you times that by RB3. So you have this equals that. Hopefully I've convinced you of that. Or another way to look at it is M3 could equal the tangential force here, okay, times R3, not RB3, but R3, because R3 is the radius of the green one. So you times that force by that, then that's going to be M3. And we know F tangential is this, so plug that in there, and you get that. Okay? So by getting these, you know these two are equal, because they're both equal M3. So if you set them equal, then you can start getting these relationships. Okay? You can find that RB, right, well, you can, yeah, right. So you can find that, so if you take this and divide it by that, you get, if you take this divided by that and flip those on that side, you get this one. And if you do the same thing with this stuff, you get this. Okay, and that proves that you know that this equals this from up here. Okay, here's R2, R3 is up there. RB2, RB3 is there. Okay, and so again, we know that this equals up there. Okay? Or you could set these equal, it's just do what's mathematically correct. And anyway, you'll find this. So now remember, that ratio is only true for quasi-static scenarios. If you imagine one of these locked down and you're putting an M2 on this and nothing's moving, what is the M3 on that? If this one's bolted down and you crank that, the M3, the ratio of those is going to equal the first order kinematic coefficient. Okay? So that's interesting. That's another interesting ratio. And that, by the way, tells you that, well, first of all, before I make this point that just popped up, I just want to explain. Notice that omega 3 divided by omega 2 equals m2 divided by m3, where those are switched. Okay, so you can think, first of all, that proves conservation of power, right? You times omega 2 by m2 and times m3 by omega 3. That's moment times angular velocity is power in, and that equals power out, is what we're basically saying. And there's no losses in that equation because it's quasi-static. This is only true for quasi-static scenarios. So we just proved that m2 times omega 2 equals m3 times omega 3, which also means that and by the way, this ratio is n2 divided by n3. So the small gear that has the fewer teeth, okay, is always going to go much faster than the big gear with a lot of teeth. So n2 is small, n3 is large, so this ratio is small, which means omega 3 is small and omega 2 is large. So you imagine the small tooth is always going fast and this is going much slower. But conversely, this one, even though it has a higher speed, has a much lower torque than this one. So if you put a moment or torque on this, you can amplify the moment or torque here. And that just comes from conservation of power. Of course, the one with the higher speed is going to have the lower torque, and the one with the lower speed is going to have the higher torque. So you can either, you can't step both up in nature with mechanical advantage and geometric advantage. You're either going to, step up the speed while you step down the torque, or you're going to step up the torque and step down the speed. Okay, so that comes from this. But now back to this point. Notice all the 2's are on top and all the 3's are on bottom except omega. The omega flips it. The 3's on top and the 2's on the bottom. Okay, and so that's very much at the heart of what I just explained with conservation of power. Okay, so now we're ready to use the teeth ratio. You can find the driven angular velocity of gear 3, which is the output, as a function of the driving angular velocity of gear 2 as the input. Okay, so remember, of all these ratios, if I just handed you a gear set and I said, find the angular velocity ratio or find the moment ratio, you're not going to want to be measuring the radius, circumference, diameter of either the pitch or base circles. You're going to want to count the teeth. Okay, so if you just count the teeth on 2 and divide it by the number of teeth on 3, then you're going to get this ratio, times it by omega 2 right here, and you get omega 3. Okay. Okay, so but now let's do something a little more interesting. What is the driven angular velocity of gear 4 as a function of the driving angular velocity of gear 3? Okay. Okay, so this one's the driving one, that's the input, and this one's driven by this one, but this one's also driving this one, and this one's driven by this one, okay? So what you could do is you know that if you have omega 3 and you times it by this ratio of number of teeth on 3 divided by number of teeth on 4, you're going to get omega 4. So if you want to find, well, what's the ratio of omega 2 to omega 4? Well, if you take this and plug it in, right here equals omega 3, plug it in there, you're going to get this equation to relate omega 2 to omega 4. And interestingly enough, the n3 just cancels, which means like this gear is kind of totally irrelevant. Any gear in between the input and the output that you're interested in is just kind of causing more distance between these things. It's not doing anything to the transmission ratio. To find it, you just count the teeth on this, count the teeth on this, ignore the teeth on this, and you take those ratios and you got it. Okay? So consider a large series of spur gears where this is the input up here, 2, 3, 4, 5, 6, all the way to 7. Okay? Suppose gear 2 is the input, gear 7 is the output. Calculate the angular velocity of a function of the number of teeth on each gear, and the angular velocity of the input gear. Okay? So what you could do is just put, you'd count all these, 2, 3, 4, 5, and 6, which are by the way, all the driving gears, 2 drives 3, 3 drives 4, 4 drives 5, 5 drives 6, 6 drives 7. Those are all the driving gears. And then you put the divided by the ratio of all the driven gears. 3 is driven by 2, 4 is driven by 3, 5 is driven, all the way to 7 is driven by 6. You do all that, and you'll find they all just cancel, right? And all that matters is the number of teeth on 2 and on the number of teeth on 7. You take that ratio, and that's how you relate omega 7 to omega 2. So, anyone that does this is not terribly intelligent. I mean, there might be one reason to do this, but really, the only reason, there's going to be a lot of energy losses between each gear. So the more gears you use, first of all, there's friction, about its axis that it's rotating, but there's more importantly sliding friction going on in the teeth as they go through their mesh. Right? And so they're going to be very energy inefficient to do this, and you're not getting any geometric advantage or anything from any of these intermediate gears. It's just the number of teeth here and the number of teeth here determine the ratio, the angular velocity ratio. So the only reason I would ever imagine anyone doing this, putting a bunch of gears in a serial chain like this, is if you really want to increase the axis difference between 2 and 7. Certainly you'd never curve it like this, right? You'd want to put it in a nice straight line, and that way you would increase the distance between the axes of the two parallel, the two parallel axes you want to achieve with the gears, but you do so without having giant gear radii. So you could spread any 2 gears out as far as you want, and they would still mesh as long as their radii are huge. They'd take up a lot of space. So the way you could get rid of that space and still have hugely far apart parallel axes is to make the gears small and put a bunch of intermediate gears. So that's the only reason you'd ever want to do this. But usually that's pretty stupid. You wouldn't want to do it, okay? And you're not getting anything mechanical advantage or geometric advantage from it at all. You're just doing a lot of friction, okay? Okay, this is essentially what I just explained. Okay, so anytime you put gears in series like this, you basically just count the product of all the driving, the number of teeth on all the driving gears, and divide it by the product of all the number of teeth of the driven gears. Okay, and note that like 6 is both driving 7, but it's also being driven by 5. So that's what you think of by driving and driven. Okay, but really only 2 is driving and only 7 is being driven. That's why they survive. Okay. But here's where gear trains get interesting, okay? Someone was smart enough to realize, well, wait a minute. What if I fuse 2 gears together on the same axis? Like 3 and 4 are stuck on the same axis, and they're constrained to rotate with the same angular velocity. That means omega 3 is the same as omega 4. Well, now what happens here? Well, if you do this, then what you find is, let's multiply, let's see, what are the driving gears? 2 is driving 3, so you put N2 on the top there, okay? And is 3 driving anything? No, 3 is not driving anything. 3 is not a driving gear. 4 is driving 5, so you'd also put 4 up there. So those are the 2 driving gears, okay? Now let's do the driven gears. Well, 3 is being driven by 2, so you put 3 there, okay? 4 is not being driven really by anything. But 5 is a driven gear driven by 4. So you put that down there. So by using this trick, you basically find that nothing cancels, and you can do incredible things with the ratio of input to output angular velocity, okay? So if you make 2 and 4 very small, which we've done here, that means there's few teeth, and then you make 3 and 5 huge, and there's space because 3 is behind 5, right? Then this gets huge, and now this number is a tiny number. So you could put in a huge omega 2 and step it down and get a tiny omega 5. So this would be screaming fast, and this would just barely be moving. And the advantage of that is it would, by that power argument, have a huge torque. So you'd step up your mechanical advantage hugely, and you would be cranking giant. You'd be able to, you could, with a very weak input torque, you could, break something off with a giant moment there. Okay. So, by the way, there's a really cool. My favorite museum exhibit is at well, I guess it's in a couple of museums. In the MIT Mechanical Museum, but it's also in the Exploratorium in San Francisco. They have these really cool machines where they have these gear trains where the first gear they have a motor stuck to it and it's just rotating, and it just rotates all day and night. And you can watch, it steps down, this one's a little slower, then it steps down, the other one's a little slower, it steps down, the other one's a little slower, till finally at the end of the gear chain, the final gear has been designed to rotate like once every million years or something crazy. And so they basically, that's so negligible speed, they bolt it down. And it's really cool to watch, just watch this continuous motion go to stopped. And it kind of trips with your brain a little bit, seeing that, how does this work? How does motion just suddenly disappear? But of course, there's a giant torque on that bolt. But it probably won't break it anytime soon because it takes like a million years or something, whatever they calculated. So it's a cool exhibit. Okay. Okay, so unlike when you put just gears in series, when you use this trick, you actually get to use everything. No gear is wasted, the number of teeth. Okay? So this is a smart idea to get very powerful transmissions. Okay. Okay, so this next topic is a little tricky. We're going to talk about kinematic coefficients and rolling contact, okay? So let's first look at external gears that are rolling on each other. And I want you to first imagine there's like an arm linking the centers of these two guys fixed. Imagine there's another link that's pinned there and a link that's pinned there. So it's like kind of, it itself can rotate around this. And these gears are rotating, okay? And of course, we're just drawing the pitch circles. These are skeleton diagrams. Imagine there's teeth on there. But they can be very difficult to visualize. If I said, pretend this one's rotating this way and this arm thing is rotating this way, what direction is that other gear rotating? It can get very confusing very quickly. So let's figure out the math of this so we can get to the bottom of it, okay? So consider the two external gears, J and K, where this one's J and that one's K, okay? And they contact at point C with rolling contact only. So there's no sliding here. This is just gears rolling contact. Now, again, remember gears the teeth are actually sliding and rolling except when they hit the pitch point. But for skeleton diagrams, obviously they can't slide or they'd shear off the teeth. So they're rolling only. It's a J1 joint, okay? Suppose we draw vectors Rj and Rk from the center of the gears to a point on their pitch circles. The magnitudes of these vectors are the radii of the gears, obviously, rho j and rho k, and their directions are described by angles theta j and theta k. So, if you draw the tail, horizontal line, go up there, that describes the rotation. These are 2 points on j, and this captures the rotation of that. And same thing with this. This one captures, this theta k captures the rotation of gear K, okay? Now suppose we draw another vector RJK that goes from here to there, okay? Its magnitude is rho C, where of course rho C is rho J plus rho K. It's the radius of this plus the radius of this is the magnitude of that. And it has its own rotation, okay? So notice this one's not constrained. If you imagine a link encompassing that, it's not constrained to rotate the same as J or K. It has its own rotation. You draw horizontal line there and go up there, which is essentially what's going on there. It's theta C. Okay. Okay. So that's the and of course it always passes through the C point where they touch here. Okay. Okay, so let's do some math and figure out how we can define the relationship between all these theta j, theta k, theta c for external gears, okay? Okay, we're going to just assume point O is held fixed. We're going to calculate the velocity of point C on both gears, okay? And we know that velocity of both gears at this point, because it's rolling only, There's rolling only contact because these are gears, of course. We know rolling only contact where they touch, the velocity is the same. Remember from the lecture, if they're different along the normal, they'll pass through each other, so you can't do that. And if they're different along the tangent, they're sliding, so they can't do that. So since the velocity in both components is the same, the velocity is the same. And that's, of course, the instant center between J and K is C, where they have the same velocity. So since you know they have the same velocity there, let's find the velocity there. Okay? First, let's use the velocity difference equation, march from O to this point here. Okay? It looks like we've defined it U. Okay, so the velocity here is 0. And so now what we do is we take omega j, okay, omega c actually, right? Because we're imagining that fixed, and we're going from this bar to that point. So this point and this point are 2 points on the same bar that links those, and the angular velocity of that bar that is not drawn here, but I want you to visualize, is omega c. Okay, so we take 0 plus omega c cross rjk, and of course, since it's planar and there's a cross product and perpendicular, it's just omega c rho c. Okay, where rho c is defined here. It's the length, it's the magnitude of that. Okay, so that's the velocity of point U, and it would go in that direction. Okay, so now we've gone from a point on this bar to another point on that bar using the velocity difference. Now that's going to be the velocity of that same point U on K, and we want to find what's the velocity of C on K. Well, we use the velocity difference equation again, and we add this velocity plus omega K, okay, cross RK, except where RK points from there to there. Okay, and so what we'd end up getting is, first of all, omega k out at you cross RK going from there to there is going to be a velocity in that direction. Okay, and that's omega k rho k, that's the scalar value, but it's going to be in the negative direction from this guy, which is in the positive direction. There you see in green. Okay, that's why you subtract them. So you're going to add this to the negative of this, because it's going the opposite direction. And now this will be the absolute value of the velocity of point C on K. Okay? And now let's find the magnitude of the velocity of point C on J. This one's easy. Okay? This point has a velocity of 0, and now it's omega j cross rj, where not this rj, but velocity vector pointing from there to that point, C, and that'll just be omega j rho j as a scalar, okay? And because they're the instant center, because C is the instant center, has the same velocity, it's rolling contact, you can equate these two. So let's do that up here. That's what we're saying. These are equal. So we're going to set those equal. And I want you to remember that rho C equals rho j plus rho k. Now, try and find the relationship between rho k to rho j. Write out a ratio, rho k to rho j, and I want you to schmooze these equations, move stuff around, massage them how you want, and find the ratio of rho k to rho j. Put me on pause, and I'll give you the answer when you come back. Okay, so that answer is this. Now, you might have put the negative sign on the other side, because I didn't tell you to find negative rho k over rho j, but I want you to have the negative sign on this side, okay? Hopefully you got something like that. Okay, and you'll find this, we're getting close to the relationship we want here. Let's do this in terms of kinematic coefficients, though. Isn't it true that whatever the input is, omega input, times the first order kinematic coefficient of this is going to be omega c? And that times this is going to be omega j, and that times this, and that times that is going to be this. So stare at this for a little bit and convince yourself that that's true. Whatever the input is, whether the input is j, k, or c, which is that link that joins these 2 points and holds them kind of together, that, whatever it is, if it's omega input, this will be the first order kinematic coefficient. Okay, and then of course these guys will cancel, so you could write this whole relationship like this. I basically just converted from angular velocities to first order kinematic coefficients, which are of course very similar. They're just instead of the derivative with respect to time, they're the derivative with respect to the input variable. Okay? And this is the one I want you to memorize. Okay? For external gears, this tells you everything you need to know, except, look, J's on top here, J's on the bottom here, K's on top here, K's on the bottom here, and then this is the special C, that's the